All right, recording is rolling. It is Wednesday, November 1st. We got the special schedule today. It's going to be the first of these resiliency Wednesdays. We're going to do this every Wednesday until spring break. I'm told is the plan. All right. We're going to do a preview of the lab tomorrow. And tomorrow we're doing mechanical advantage lab. But I'm going to give you guys most of the class today, just solve physics puzzles. Yesterday, I showed you guys how to set up most of them. I think we did all except like the last couple looked at. Maybe we'll look those over real fast for give you guys some independent time. Right? There's always a bunch of physics puzzles that I give you guys that I just don't circle because I'm not really assigning them. But guys, the more time you spend with any subject, the better you're going to get at it. So feel free always to venture off and solve some of these that it just won't circle. Right? It's always extra opportunities. Right? So those puzzles, let's have those do a couple of days. I'll get you guys your energy quiz by the end of today. Now, today, I really just want you guys to full focus on these physics puzzles, but I do have your quiz printed out, so I'll get you guys before you walk out the door today. Let's have it due on Monday. And then, yeah, we got the special schedule going on with results due Wednesday, right? So let's look at Mechanical Advantage Lab. I got a video demo for you guys. Switch my screen here. This over. Okay, let me switch it on Zoom. Switch. All right, here we go. The pulley. Yeah. But she's like 3 times as strong, right? So you guys see 2 fixed pulleys here and a movable pulley here, right? And there's like 3 ropes going up. If you look at the movable pulley and see, well, how many ropes are going up, right? Like if that pail weighs 300 newtons, for example, then doesn't that weight effectively get split 3 different ways? So what's the tension in the rope? 100 newtons, right? Because pail weighs 300, divided by 3, 100 newtons. So she's only pulling with 100 newtons. Now the catch is she pulls 3 meters of rope and the bucket only moves up 1 meter at a time, right? So let's bring that back over here. So some more details, right? Now, right at the beginning of the video, they mentioned a bunch of different simple machines. Here's like a full list of different types of simple machines. Okay. I'm going to focus on this one, which is the same thing as the lab tomorrow. Have you guys focus on that one? Okay. So let's get a detailed look at that. Now, in class here in front of me, I have a 5-to-1 rigged up. So this 1 kilogram lab mass weighs 10 newtons, but the spring scale over here on the opposite end is only reading 2 newtons. You only need 2 newtons to lift 10 newtons, right? Guess that the small guy beats the big guy, right? Because weight split by, right? Now here's my cartoon version where I'm showing a 3-to-1 mechanical advantage, right? So you guys get like that, right? Okay. Now, this 3-to-1 mechanical advantage is really what's called an ideal mechanical advantage. I have 2 different perspectives on mechanical advantage here, which is going to be 2 slightly different numbers. Okay? The ideal mechanical advantage is based on the geometry, right? So okay, I see like a 3-to-1 ratio, right? I bet if you pull this some distance, if you pull like 30 centimeters, this might move up 10 centimeters, 3-to-1 ratio, right? Okay? But the actual mechanical advantage is, well, what factor are you actually multiplying your strength, right? Because it might be actually a little bit less than 3-to-1 for a couple of reasons. And maybe there's a little bit of frictional loss. Maybe if these strings aren't exactly vertical, you play out the trigonometry, you're not going to get the full 3-to-1, right? So maybe it comes out to like the ratio of these forces might be like 2.7 to 1 or something like that, right? It's a little bit loss process. Right? Another thing you do is you can take the ratio of those mechanical advantages, right? That divided by that, you can get efficiency percentage. Like maybe it's like 90% efficiency, right? Right. And what's the one of the guiding principles to make this whole thing work is actually a conservation of energy type approach. The work output can only be ever as much as the work input, and this is assuming 100% efficiency, right? So a small force times a large distance pulled would equate to a large output force, like a large weight being pulled up just a little bit at a time, right? So work input equals work output. So it's kind of a conservation of energy concept there. Okay? Now, tomorrow, what we have you guys do is rig up different type pulley systems. Try it 1-to-1, 2-to-1, 3-to-1, 4-to-1. Right? And then measure all these values. So what's the input and output force, right? So you got the weight here versus the spring scale rating. Right? And then distances. If you hold a ruler up, say like how far does this move up versus right, how far are you pulling, right? Record those numbers. Then you can calculate what's your ideal versus actual mechanical advantage. Right? The ideal is just based on the picture, but the actual is you take the ratios of the forces, right? I should have another row on here for efficiency. That would probably be a good thing to keep track of too, right? How efficient, right? You can do that either by dividing the mechanical advantages or doing work out compared to work in. It ends up being the same ratio at the end, right? So tomorrow, I'll have you guys take out a blank piece of paper. Actually, I might just leave this up the rest of the class. Well, the last half of class anyway. So if you want to get a head start, you can divvy the paper into quadrants, set up one of each mechanical advantage. I'm going to have you guys draw the pulley system that you're making, and then record these numbers, right? Do some calculations, right? So that'll be our main focus tomorrow, and then Friday I'll have an FRQ for you guys. Okay? So, all right, physics puzzles, because we have covered I think all these except the last couple. So here I'll go over these at least with you guys verbally. You guys do know the solutions have been posted to Classroom for a while, so if you have your laptop, you can access those. Okay? I think we were in kind of near the end of number 53 when the bell rang yesterday, so let's quick look at that. Okay. Electric motor to accelerate train from rest to some speed and some time. Ooh, 21 milliseconds. If you've been paying close attention, this conservation of energy section, time hardly ever shows up as a variable. Time is not in any of the equations for energy, right? So we haven't really seen time there, right? But I see why they're giving us a time value, because the question is what's the average power, and power is work per time. Right? He gives the mass of the train in grams, ooh, right? So here's how I might step through this. I think this is like half in your notes from yesterday. Right? Well, I know the question is power. I know power is work per time, right? It's a rate of energy transfer. Right? But isn't work force times distance? Force times distance. Right? So it'd be like that, right? Now they told you starting from rest goes to some speed and some time. Right? That sounds really kinematic, right? Like they didn't tell you the distance or the force, right? But they did tell you the time, right? So let's do a tax VV checklist. Tax VV, right? What did they give you? What could you possibly want to be solving for to answer this question? Right, A and X. Yeah. Because they said start from rest, so that's 0 meters per second there. Bing, you got that. They told you how fast it goes to. Bing. And they told you how much time. Bing. Right? I mean, I have to convert milliseconds to seconds, but basically you have this, right? So you could solve for acceleration, you could solve for displacement. So you have to go way back to unit 1, break out these kinematic formulas, right? You guys can do that? You guys can do that? Okay. So it is solvable. Like you could figure out how far and what's the acceleration, right? So let's go back to the main problem we're trying to answer. Well, or now what? Oh, guys, force. Force is equal to what times what? F equals mass times acceleration. F equals ma. Newton's second law of motion. The distance, maybe I'll just call it x to be consistent. Right. And okay, they gave you the mass of the train. Have to convert it to kilograms or whatever. Right? Acceleration, you can solve for using kinematic. Got that? How far the train goes, you can also solve with kinematic. And they told you the time in milliseconds, probably convert to seconds first would be a good idea. All right, so in principle, you could solve for the power. And hey, guys, what's the unit for power? When you're going to get a number in your calculator, that's some number of what? Watts. Right. So remember, power is measured in watts. Right. And 1 watt is equal to 1 what per what? Joule per second, right? Because it's like a rate of work, rate of energy, joule per second. Okay, number 60, let's get real fast. Object has some mass, it's subject to some force. Ooh, you guys see that force versus distance graph right there, force versus distance. Whenever you see a force versus distance, okay, the first thing I would start to be thinking of is that's probably related to this poster right here. Right? Look, force versus distance. Now here, this poster I'm showing a constant force, just very simply a constant force. But you guys know force times distance is an energy transfer, that's work, right? That's how I defined work, right? Okay, so if it was a constant force, that would very simply be the area of that rectangle, right? Right. So what if you have a variable force like they do on number 60, right? Well, is it still the area under the curve? Yeah, it's probably the area of that trapezoid. Can you split that up into a triangle, or rectangle, and triangle, right? Find the work. Right. Side note here, if you're in class, do you guys see those posters over there on the wall with the blue banners? You guys see the one that says impulse on it? Oh, guys, what variables are on that impulse poster over there? Force versus what? Time, right? We're going to talk about that next week. So the area under that curve represents a change in momentum, which is like a change in mass times velocity, right? Which is, that's a next week concept, right? All over the place in AP exams, you see graphs that are force versus distance and force versus time. Force versus distance, you're thinking about energy, work. If you see force versus time, which you will next week, you think of it something to do with like impulse, momentum. Okay. All right, so what else we got here? Find the work done as it moves from these different locations. Right. Oh, and then finally, the last question says something about its speed. Like, can you find something about speed? Well, if I want to know something about speed based on work, you guys remember sum of energy initial plus work equals sum of energy final, right? That could be like for an open system. That could be an open system, right? If somebody's subject to a force, I bet you have to use this framework. Right? Here's the area under the curve, right? So you would have solved that already. If it starts from rest, this would be 0. If it didn't start from rest, maybe it starts off with some 1/2 mv0 squared, for example. I'm just making it really generic, right? Then you add the work done, some kind of force times distance, right? And if it's a variable force, I guess it's like an integral type thing, right? And then, have you guys done integrals in calculus yet? Oh yeah. All right, yeah. So you basically just like add up the area under the curve, right? I guess dot dx or whatever. And then you'll end up with some 1/2 mv final squared. And the question is like, how fast is it moving at the final location, right? You guys can figure that out. If it starts from rest, this term 0. Okay. Yeah, integration is just the area of that trapezoid. That's all it is, right? Right. So that's just fancy notation for.
I'm just asking you to integrate the whole thing.
Well, up to whatever it tells you to do. Like if it says go to the 15-meter mark, then yeah, 15 meters would be the whole thing. Yeah, because 0 to 15. Right? There's a term that's called the work energy theorem, which says that whatever work that you put into something, which is this right here, just goes into its energy. And if it's not changing height, then it's all kinetic energy. So it would all eventually round to like a change of speed. Right? Right, and last one. Tarzan swinging on a vine. Angle so many degrees from the vertical. Ooh, that looks like a 3, 4, 5 geometry angle, doesn't it? Okay. What's the speed at the bottom of the string swing if he starts from rest or if he pushes off at some speed? That's pretty solid for you on this poster, isn't it? Right? Now, guys, should you be able to break out a blank piece of paper and do this entire thing from scratch? Can you guys do that? Right? I think I've walked through this with you guys at least a couple of times, right? Right. So it boils down like really big framework. This is the same as Galileo dropping the ball off the tower, right? Tower some height, there's some crash speed at the bottom. It works out the same, right? So the speed at the bottom is still square root 2gh, but the extra fun of the pendulum swing is you have to figure out, well, what is that height change? You figure it out from geometry. Here's L cosine theta. So the height change is the difference between the full L and the L cosine theta. That's that. You can factor out the L if you like, right? And then if you push off, right, then you have to start with an extra kinetic energy term. Okay? But notice how that's going to end up in the end. I put it in light gray text so you can ignore it if he starts from rest, but if there's some value, then you have to include it. Right? Notice you don't say final speed is initial speed plus square root 2gh. You have to do final speed is a giant square root. You have to do the initial speed squared plus 2gh, right? See how it ends up on the inside, right? I just skipped a few algebra steps from here to here, but you guys can figure that out, right? Right? If you guys see an FRQ that involves a pendulum, are you guys going to start with this step? And then you're going to write this, and you're going to include a couple of other algebra steps so you end up with this. Right? You guys can do that all in terms of variables. Okay. All right. So that's all the ones I assigned. Oh no, sorry. There's one more. Oops, I almost missed this guy. 89. All right. 3 masses. Modify that would. After it moves some distance, what is the speed after moving some distance? Right. You guys have 2 different ways to solve outputs now. You can do dynamics followed by kinematics. So you can solve for what's the acceleration, and then after especially if they said how much time is it moved for, I would probably do that method. After it's moved so much time, how fast is it moving, right? Or if it says how much distance, you could also use that method too, right? Dynamics followed by kinematics. So what's the acceleration net force on total mass, followed by kinematic motion, right? Or you can do conservation of energy approach. Let's just do this one verbally, right? So what's supplying the energy? Is the large weight falling supplying all the potential energy, right? MGH. And that's going to go into several places. It has to go into lifting the small weight and giving every single one of these a speed, which is kinetic energy. So that energy goes a bunch of different places. I think I have a poster for that too. Let me see if I can take it real fast. Well, here's a classic Atwood. While you guys are looking at that, let me see if I can find my modified version. I have got somewhere in here. Here it is. Here it is. Modify that with energy. That sure does look a lot like that textbook question, doesn't it? Okay. So the large mass falling supplies all the potential energy, right? And it goes into lifting the small block and giving each of the 3 blocks of speed. Right? If there's friction here, then this would be an open system, in which case you'd have to subtract force and distance out of it, right? Right? If there's friction, right? Can you guys figure that out?
Can you show me the equation for 60 against the end?
Number 60. Okay, so yeah, number 60. If you want to figure out the work under force versus distance, you just break it into a triangle, a rectangle, and a triangle for the trapezoid. You add up those areas, right? So like areas of triangles, right? And then here's your work energy theorem. Did they say it starts from rest? If the object, oh no, it doesn't start from rest. Okay, so you do have to use this full thing, right? Just read the question, right? So they did give you an initial speed at the starting point. So you have to use this whole thing. It starts out with some kinetic energy. And you say plus the area of that trapezoid, which is what that is. Right? And that'll end up with some different kinetic energy at the end. And then if you pop in the mass of the train, what did they give the mass in terms of? They tell you 3 kilograms. Okay, so they told you the mass in kilograms. So that's nice. It's already in base SI units. Okay. Right? Right. You guys good? Let's check our schedule here. Okay, we're gonna. Okay, we have a solid 17 minutes. It looks like, right? So.
89 was the equation since friction on the
Okay, yeah, guys, if friction is equal to 0, for 89, the question is, right? Guys, if friction is equal to 0, then doesn't this orange term just go away?
And it's just MC.
Yeah. So if it's like a frictionless tabletop, suppose there's like an air hockey table up here, right? And it's just, right. So there's 0 friction. Yeah. The heavy one falling is supplying all of the energy.
Yeah. So that's the one side.
Right. So that's right. That's the sum of energy neutral, right?
And then the other side,
everything else, right? Right, has to lift this and give every single one. Yeah, what are you solving for? Number 89 says find the speed after it's moved 4 meters. So if it says find the speed after 4 meters, then this height fall is 4 meters, and this is also 4 meters, 4 meters to 4 meters. And you're solving for speed, so you have to solve for this v. And it's all the same v.
Because they're all.
Yeah, because they're all tied together with string, right? Yeah, yeah. So you can like factor that out, solve for it. Okay. All right. Yeah, good question there. Good check. Right. So yeah, I do want to give you guys the rest of class to work on these puzzles. If you've solved all those circled ones already, then start taking a look at the ones that aren't circled. And then last couple minutes of class, I'll get the next quiz in your hands, and that'll be due on Monday. Okay. All right. So there you go. So we got. Let's leave that there. Oh, actually, where's tomorrow's lab? Here it is. Right. I'm gonna leave this up here for tomorrow's lab, and then yeah, just stop the video there. If you have any questions, let me know. Give you guys some independent time to work.